Okay, so this video is going to cover the topic of average value from section 6.2. So I think it's at the bottom of your notes from 6.2. So we talked about area and volume, and then we did the sort of beginning part of 6.2, but this is sort of just an extra topic in 6.2 that I thought would be pretty good for this video because it's pretty straightforward in terms of what you're actually asked to do. So our whole lives, or as far as I can remember, we've been calculating averages. And we all hopefully remember how to calculate an average. So if you're given n numbers, finding the average is pretty straightforward in terms of you add all those numbers up, y1 plus y2 plus dot dot dot, and you add all those things up, and then we divide by n. And that's how we calculate an average of n numbers. We've done that, for quite some time. I don't know when you learned that, but I feel like we've always known how to calculate an average. But now we're going to do something a little bit different. We want to calculate the average value of a function on a particular interval. So how do we calculate the average value of a function on a particular interval? That's the question. That's what we're going to try to answer today. So the idea is still the same. We want to take a whole bunch of values of the function, and we'll take f of x1 star. We'll use that as our sort of guesstimate. We just take a whole bunch of values. We'll take n of them from our function, add them all up, and divide by n. So that's that same sort of idea. And then, as a reminder, from when we were doing something over an interval, that should hopefully sound familiar when we talk about integrals. Delta x, remember, was b minus a over n, which tells us that n is really the same as b minus a divided by delta x if we solve that equation. So if we want to rewrite this, we could replace this n with this equation, and we get that this is really 1 over, if you do some algebra, 1 over b minus a, so that's taking out the n and putting that down there, and then you have f of x1 star plus f of x2 star, and then you add all those up down to f of xn star. And all of that is also times delta x. Right, so there's a delta x as well. That's from the bottom part of this fraction. So the fraction sort of gets flipped, right, because n is in the denominator. So b minus a goes in the denominator, delta x goes in the numerator. So we now have this equation. We can distribute that delta x into the equation so that each one gets a delta x. And we can rewrite that as 1 over b minus a, the sum of f of xi star delta x. And that's I equals 1 to n. Okay, so that's that summation notation from when we talked about integrals the very first time. And then the idea is we want the average value of the function. We only took n values, right? But a function has an infinite amount of values. So it doesn't just have the values of not just like values at 1, 3, and 5. There are values at every number between 1, 3, and 5. So what we want to do is take this n and think about taking the limit as n goes to infinity of 1 over b minus a, the sum, I equals 1 to n, of f of xi, delta x. And if we take that limit, by definition, if you remember, 1 over b minus a, that doesn't change as n goes to infinity. But this piece right here, the summation part, if you remember Riemann sums, that by definition is the integral from a to b of f of x dx. So we get this nice formula for average value of a function, and the reason I worked it out above is so you can see actually where that formula comes from instead of just me giving you the formula. But the idea of the formula is the average value of an integrable function on an interval from a to b. You just do 1 over b minus a, integrate from a to b f of x dx, and that's going to give you the average value of that function over the whole interval. And so hopefully you can kind of see where that comes from by looking at this example up here. We first just took n points, added them all up, divided by n. That's the general idea for average. And then we had to ask ourselves, what happens as n goes to infinity? And as n goes to infinity, we get the full value of the function. And as n goes to infinity, we recognize that as an integral. And that, by definition, is our average value function that we'll use to calculate average values. Okay, so I wanted to work an example. The example in your notes is actually something we can't do, so I'm going to change it. Find the average value of, we're going to change this ln of x to cosine of x on the interval from 0 to pi over 2. So that's a slight edit in your notes. So we'll do this problem, which we can do, and it will make more sense. So the first thing we're going to want to do in order to calculate that average value is to do 1 over b minus a, integral from a to b, of the function itself dx. So using some algebra, this is just 1 over pi over 2, which is the same as 2 over pi. And then the integral from 0 to pi over 2 of cosine should be, I believe that's sine of x. And we evaluate that from 0 to pi over 2. And then we just plug these numbers in. We get 2 over pi, sine of pi over 2, and then minus sine of 0. And then I think that sine of pi over 2 is 1 minus 0. So we get 2 over pi as our final answer for the average value of cosine of x on the interval from 0 to pi over 2. Okay, one more quick idea related to average value is this mean value theorem for integrals. And I'm not going to actually prove this, but I do want us to look at it geometrically and think about why this makes sense. So we talk about having a continuous function on an interval from a to b, and then the theorem says that there's going to exist some value c in our interval from a to b, where f of c is going to actually equal the average value of our function, which is that formula 1 over b minus a, interval a to b of f of x. So this is our mean value theorem for integrals. The idea that at some point there is a c such that the value of the function at that value is equal to the average value at some point. And if we rewrite this as f of c times b minus a is equal to the integral from a to b of f of x dx. And if you remember the mean value theorem that you did in Cal 1, when you're, I think hopefully some of you may have proved that in class, you actually did go through a similar process where you took the denominator out. And once we do that, we can see sort of graphically, hopefully, what's really happening here. So we have an a, we have a b, and then you have some function. So maybe it looks something like this, who knows. And then at some point you're going to find a c, right? And if you look at this side of the equation, f of c times b minus a, well, here's f of c, correct? This value right here. So this is f of c. So you can think of that as f of c, and then b minus a is this distance from here to here. So really what this f of c times b minus a, that's really the area, right, of this rectangle, okay? So this side of the equation, this left-hand side, is really this rectangle. And what that's saying is that at some point the area of that rectangle is equal to the entire area under this curve. So this whole area here is at some point, right, equal to the area of a rectangle that somehow fits within the interval from a to b. So that's the visual representation of what this integral actually is. We're not going to prove this particular theorem, but I thought the visual would help. So really what it's saying is that at some point in your interval from a to b, there's a number where if you calculate the area of that rectangle at that number using that as the height, the width is always going to be from b to a, the area of that rectangle will equal the area under your full curve from a to b. So that's the idea of the mean value theorem for integrals. We'll work one example, and then we should be good with the mean value theorem for integrals. So here's our one example. We want to find a c such that the average value of our function that we did in part b is equal to f of c. So if you remember, f of x was cosine of x, and we got that the average value for that one was 2 over pi. So what all this is asking us to do is to find, we take the average value, which is 2 over pi, and we want to set that equal to f of c, and we want to find c. And the way we would do that is 2 over pi is equal to cosine of some c. And then to solve for c, remember you would take the inverse of both sides, which is cosine inverse. So if you take cosine inverse of cosine of c, you'll get c is equal, and then this is just a calculator question. So punch this into your calculator, This guy, you cannot calculate that by hand. No one should be able to do that. I got 0.8806, and that would be my value for C.